welcome everyone. Please, as you're coming on in, do utilise the chat feature that we have today. Say hello and let us know where you're joining us from. For those that don't know, I'm Adele Lewis, co-organiser of the Shift Left Reliability Meetup. We'd love to obviously share, we're going to be sharing the recording with you after as well. And we'd also like to invite you to our Slack community. So we'll share that a little bit later on after the demo. If you do have any questions throughout, please do post them on the chat, and we're going to make sure that there's time for some Q&A after. So maybe we can get started. I can see there are more people joining. Welcome. Sylvain, over to you.
Well, thank you very much, Adele, for setting up this event. It's very nice of you. It's well done as usual. So thank you very much, Adele. Hi, everyone. So we've got how long? Like an hour or 45 minutes? Yeah, 45 minutes, do we? All right. So I really need to be concise. Okay. So today we're going to talk about chaos engineering. As I was saying a little before, it'll be my understanding of chaos engineering. Not that it's a definitive approach or anything. It's one, and I hope you'll find it interesting and perhaps exciting for your own needs basically. So I'll start sharing my screen with obviously the mandatory bunch of slides I've prepared, which I will do my best to go through very quickly. So let's get started. So like I was saying, I'm Sylvain Leguarche. Just call me Sylvain, it's way easier, even in French. CEO of Reliably, which used to be called Chaos IQ, if you knew us by that name. I co-created Chaos Toolkit with Russ Miles, and I'm currently the lead dev maintainer of the project. And I'm also an amateur gardener. I'm saying that because that's the only way I keep healthy and sane when coding too much. So where do we start? Well, we all change, or at least our systems do. I think in our industry, we have perhaps less so now, but for a long time, we felt that we could sort of control everything. We knew the outcome of pretty much everything. Automation, testing give us that sentiment that we've looked at every possibilities and it's going to go as planned, right? It doesn't. It's very presumptuous, if not false, assumption. Systems change all the time. Most changes are completely harmless and actually not even noticeable, right? Your bug fix is a change, obviously. Anything like that is a change. Your NAR drive going away is a change. The GitHub going away is a change, or anything like that is obviously a change. So sometimes we do initiate that when we release something new, and therefore we are attuned to look at what's going to happen, right? But most of the time we go through changes either because they're unnoticed or we just didn't plan for them, right? So that's a big problem. So we have a lot of subtle variations in our system and in our assumptions of the system that we need to tackle, because otherwise we go the wrong lane, I guess. So we have entropy in the system, and that entropy needs to be kept at a level where it's manageable in a way. So we need to make sure that things that are connected are together can become, while a forcing factor for change, that change should be at least understood or proactively explored if we don't know enough about it. So that's why we need to engineer our system. That's what I love about chaos engineering as a term, is it talks about the engineering side of things. And I think that's very critical. It says, remember, you are engineers. And as engineers, you look at things and try to provide structure, a framework, a process, however you want to name it, but something that allow you to go through that and make sense of it instead of enduring it. So we go through impacts. So like I said, we cannot eradicate change. It's going to be there. So we need to embrace it. We need to embrace the fact things are going to change. It doesn't mean YOLO, right? It doesn't mean, well, whatever happens, right? We release and we'll see what happens. No, it really means we know it's going to have an impact somehow, either users, which is the worst thing probably, or even ourselves, right, in some fashion. So ideally, because we acknowledge that, we are ready to go and start thinking about it, right? It's not even ignoring it. It's just not being aware that it happens, right? I think we have development pipelines that are extremely solid and very well understood these days, where you push something and there are steps happening. Tooling may or vary in quality, but at least there is an understanding of the concept of it. But I think the outcome is not just how it's deployed and live. It has to be, okay, it's deployed, but what does it mean really beyond that, right? What does it mean? And how does it impact the system? Or how is it impacted by the system running live? So that's what we are dealing with. So engineering here is a conversation about that change and impact. So to me, chaos engineering is change discovery. You discover the impact of the change, discover what that means. And chaos engineering is pretty great at that because it's very candid. It doesn't make assumption about the system. You may make an hypothesis, as we will see in a minute, but generally speaking, you even that is very non-assuming. That's your understanding you're stating, basically. That's my understanding of the system as it should happen, right? That's the token I have in my mind right now about the system. The reality of the system may be different, and I need to go and figure this out. So that's what you're looking at. And that's why I think it's very closely linked to SLOs in many ways, if you're into SREs. And then what chaos engineering proposes is, well, now that you have that sort of understanding of the system, why don't we change something into it and see if that understanding remains? Or how is it impacted, basically? Has it deviated from normal? And that's basically, in a gist, the whole chaos engineering mantra and philosophy. It's you have an assumption of the system, and you take it for true, and you go and explore that and see if that's actually true under certain conditions. Which also means you have to do that quite regularly, otherwise your new true may not actually hold in a week from now. So obviously that requires a lot of priorities about what matters and what doesn't, which a lot of organizations may not be mature enough to actually talk about. But that's basically where you are. You're going to end up with practical things you're going to fix, like a test, basically, you're going to figure out. But sometimes it's going to be more about conversation. All right, this happened. What does it mean for us, right? Does it mean that we picked the wrong tooling? Does it mean we picked the wrong database? Things like that are going to be the conversation enabler, basically, because you'll have the data, and that's what you're looking for. So outcomes, like we saw, fixes improvement, but to me, more importantly, it's a growing mindset among an organization, not even just engineers, but amongst the organization, that changes are not to be feared. We should embrace that. We basically changed, delivery pipeline. Basically, that's what we do. We are developing changes, if you will. So we need to figure out how that happens. And chaos engineering is one approach to do that. If the outcome is you being less stressed and reduce anxiety within teams, I think it's a big win. Tooling. Well, tooling is where usually we start, for better or worse. That's our industry, and I'm not going to, judge because I'm there as well. The first thing I go for is a tool and see if that works for me. All right, so I'm not judging at all. But tooling here is perhaps less critical than the mindset. If you're already doing load tests, QA, any sort of exploratory things, or any sort of looking at the system, basically, and so in a certain angle, you're already doing something. Right? Chaos engineering is going to be more the shiny name you're going to put on it. Perhaps more explicit, but that's going to be one more. Tooling, generally, you can split that into three main categories, I guess. The fault injection side, the thing that you use to actually impact the system. So we all know the break, on purpose philosophy, but it doesn't have to be breaking. It can just be, okay, this is a change we do on purpose regularly. Let's say we review all the tokens and we revoke them, right? Like every 30 days. How does this work, right? Because we tend to just ignore those tokens, end of life, and we go on and do something. So you could decide to react to a chaos engineering that forces revocation of token and see how the system reacts in general. So you have plenty of things, but fault injection is going to be CPU stress, like if you use stress ng on any Linux machine, network latencies. You also have anything around, if you're on cloud, anything around permissions. You remove the permission to write an S3 bucket. What does happen? How does it, ripple effect into the system? So that's any fault injection is anything that changes from normal, I guess. And we all know that configuration is one of the key ones. So usually you start there. Chaos engineering experiment, I guess this is where Chaos Toolkit fits, most of it. It's a definition that we were giving. You state normal and you do something, and then you look at normal. Is it normal again, right? That's the philosophy of the principles of chaos engineering. And chaos management, I guess, is fairly recent. It's much more about how do you deal with the gazillions, the fleet of chaos engineering experiments you have out there, and how you manage them. So it's much more about central control tower dashboards and stuff like that. So I think that's a case of Reliably, of Litmus, of Gremlin, obviously, scenarios, experiment, whatever you call those. It's that central place where you can collect all that information. So usually, if you look at tooling, you're going to have to understand each of them because they will lead you towards a certain solution or not. Finally, that's where basically I want to end this short talk. It's, to me, healthy engineering teams lead to success. We are, as an industry, sometimes, although we talk more and more about it, but I think we need to pay more attention about the sustainability of our teams, the health of our teams. It's good that we push for new features. It's good that we say, you need to do this and burn it or whatever. I don't personally like that, and I don't do that in my company. But generally speaking, what I think is stressed out teams on call, anxiety and on calls and everything like that can be, to a certain degree, I'm not saying you're going to erase all of it, but to a certain degree can be reduced. And that's going to make everyone happier, and happiness or healthiness is going to actually help the organization in the long run. So I think being proactive allows us for a bit of safety in exploring new things. I was discussing with a few companies recently where onboarding includes some sort of, first day deployment situation or first day incident, a situation. I think it's great. You remove that buildup of anxiety from the get-go and say, this is how it works here. This is real life for us, right? And I think it's important. And chaos engineering is one approach to become healthier as a team and organization. And that's why I think it's very important. It's not easy to evaluate as an ROI. So sometimes it's difficult as a discussion with management. But I think today it can't be overstated. Better teams, healthier teams will lead to better organizations. All right. Sorry for the pace. Obviously, we've got short on time, so I want to go through that. If you want to read the slides, we'll put them on probably on Meetup or somewhere, and we'll be happy to go through that again. And ask questions toward the end. I will be very happy to answer them. Right now, we're going to go back to showing a short demo of Chaos Toolkit. So Chaos Toolkit, why? Well, first of all, because I've implemented it, so I do know it quite well. I think it's also a fairly nice tool because it provides it's very extensible. You can use it in many scenarios. It's basically a command lines, sort of scenario here where you extend it the way you want and you make it do what you want. Other tools are probably more user-friendly or more formal in a way, and I think that's great. We need that. But Chaos Toolkit will basically, do whatever you want, however you want it. And I think when you start exploring your chaos engineering experiment, you realize you want to go through some scenarios that aren't necessarily provided by other platforms. So that's why I'm here. So we've got two simple things running on EKS, the Kubernetes cluster on AWS. And what we have is a consumer consuming data from the producer, and the producer is basically sending, a value, and the consumer, consumes it, and that's it. I wanted a very simple, setup, two services talking to each other, nothing complicated, nothing fancy. And we'll see that later, but they run on AKS. So basically, I've got a bunch of Prometheus and stuff like that running. So let's not show that yet. So what we're going to show now is an experiment, a simple basic experiment. So I will try to make it bigger because I don't know how much you can see it. So if it's too dark or anything, do let me know, because it's not easy for me to realize that. So what we have here is a basic Chaos Toolkit experiment. A Chaos Toolkit experiment is a JSON or YAML, pick your poison, file, right? By default, I use JSON, but it's it's just as terrible as YAML to read anyway. So this is what you have as an experiment. An experiment is a JSON file where you have a method, basically. And a method is meant of usually at least one action. In Chaos Toolkit, you have actions and probes. Actions are what others call attacks, if you will. It's a thing that you do against the system, right? The turbulence you're injecting, right? We call that action in our vocabulary. Probes are more about collecting data. It's they read the system for gathering information. So we'll not deal with probes yet. So this one is simply calling a function, an extension called Chaos Toolkit Kubernetes. So Chaos K8s, it's written in Python. And basically what we say is terminate a pod, and we're giving it a label and say, terminate any pod, at least one pod that is labeled this way. That's it. At this stage, what you have is something that impacts the system. You're not making an assumption about the system yet. You're not making a theory about the reality of things. You're just saying, can I do this against the system? And why would you want to do this one? First of all, because for the demo, it was probably the easiest one for everyone to grok. But second of all, because it does happen. You release something, you're going to have a pod terminating and one other coming up, right? So you have that opportunity on a daily basis. So if we run that, we'll see the easy failure later on. And let's play demo god is with me. So here, it was really fast because it doesn't do much. But we see underneath the container creating, and we just see that we created a new container of the producer kind. That's it. That's all we did. Great. At this stage, well, that's really not useful. Although you could run that on a daily basis, a bit like a Chaos Monkey sort of thing, right? You could automate that, and that's it. Go and tear down the pods randomly at any time. And why not? I think it's valuable to learn that. But here, during an experiment, you probably have to make an assumption about what good looks like. So we're going to move to the next one, where we introduce a steady state hypothesis. We should have used a word that a Frenchman can say. A steady state hypothesis for experiments. So what is it? Well, basically, it's all normal. What do we expect that happens, right? And here we say, we know we have a number of replicas because our pod is hooked to a deployment. So we've said we have one here. And we make assumption that we should always have one at any time. We should never actually go under one. I don't know why, but that could be the gist of our decision. Here, what we're going to do is use a probe. That's why I introduced a probe. That's going to talk to Prometheus and make a query. And here we simply looking at the query of, give me the number of pods that were in phase running for the last minute. The demo is so fast that there's no point in going further in the past. And it should never be different from the number of desired replica. And what we do is we have what we call a tolerance, which stays basically look at the result of that probe and say, go into and look at the value, and it should be 0. So basically, the difference between the two should always be 0. Otherwise, it just doesn't work. So let's run that again. That one. So here, the difference is it's going to run that hypothesis once. I'm going to pause a bit as well for the demo to happen. But basically, we run that hypothesis once, because we want to see, is a system in normal state? I can't learn from it otherwise. So I'm going to assume that it has to be in the normal state already. You can skip that, but by default, that's what it does. And then it runs the method, and it runs again the steady state and decides, has it changed? And here it tells us it has. It has changed. It's not 0. So what we've seen here is when we terminate the pod, which is quite granted, it's almost like a very, it's more for you to learn chaos engineering here through Chaos Toolkit than anything else. But here it's expected, right? You terminated the pod. So for a split moment, we didn't have the number of pod. So obviously for a service, that could mean maybe some requests weren't served at some time, right? So we could decide that maybe what we're going to do is not have one pod, but many replicas, and be perhaps a bit more loose about what that means. We could have 3 replicas and say we always need 2. Obviously, that's what Kubernetes does anyway. So with replication controller, so I think we're good. but it gives you a feeling of how we build a chaos engineering experiment here. You've got the method with at least one action. Usually you don't want more, because otherwise it's hard to know which one actually broke, if you want to see it that way, or deviated the normal. But that's it. That's what you do. Now, at that stage, it doesn't really actually tell you much about the system, to be honest. So what we're doing is we're adding a new action. And here is to show you the extensibility of Chaos Toolkit. We're not asking a Python code here. We're using a process, just a binary called DDoSify, which is a command line load injector, fantastic tool, and very nice to use, very easy. And you can just call it that way. So where we're going is inject some loads and see what happens. Oops, sorry, it's not the one I wanted. I wanted the third one. So it's going to run. So we see that in the background as a thread, we run it beyond the scene. We run that thing, and we have a new pod still created, and we're running that. Now, it's interestingly, it might not actually be helpful here, because what are we learning? We still have the same steady state hypothesis, right? And one we know is not going to actually tell us much about the system's health. We know we've lost a pod during a split second. Okay, fair enough. How did it impact the system? How did it impact our users? Well, this is, and that's the last step for this particular experiment, where the new steady state probe, yes, this one, where we say basically we're going to make a new query now and say, did we get some 500? Remember, the consumer service talks to the producer. So if the producer goes away, the consumer probably is going to error in some fashion, because it's not really well built. So obviously it's going to break. I haven't had a circuit breaker. It's on purpose that it's very dumb, I guess, here. But that would be a fixed improvement, probably. So we're going to do the same thing and just run that again. Yeah, we should be good. So now we run, and we see that we have a number of replicas went good, and the other one, which is verify error rates. Oh no, I run the same again. Well, let's stop that. It was the fourth one. Apologies. We'll see if it starts again, because it might not actually. See, that was planned. That was on purpose here. Not the error, but it's a good example. We said we look back 1 minute behind us to see if pods were deleted as the first time we ran the steady state, right? To say, can we even learn something? And because it happened less than a minute ago, the first time we ran, it immediately fails because it bails out. It says, well, we're not in a good condition to even run this experiment, so let's not do that. So we're going to just wait a few seconds so that this doesn't happen again. Right, we should be okay. Hopefully, anyway. Yes. So now we see that we didn't have any error rate recently, which is fair because we waited long enough and we just restarted. But bear in mind, we still have a load of 150 requests over 30 seconds. So we're bound to probably have one or two that are failing. So let's see. Oh, I've got my, interestingly, I've got my consumer that crashed the backup. Well, that's good because it showed me, see, it's interesting because when I planned that experiment, I ran with a few more consumer services. And I don't know why I reduced that. And here we have one pod only. And when I prepared the demo, because I had 3 consumer replicas, they could take the load I was injecting. But here with one, it couldn't. So it crashed back off. So it shows you a chaos experiment can actually show you other things that you didn't plan for in the experiment itself. So it's pretty nice. And basically that's where it fails because it's the number of pods failed anyway. So we're going to actually increase that. Otherwise, we can't do the demo as we want. We're going to put more consumers. Oops, maybe not 34. It's All right, so we should see 2 more consumers. So hopefully, even if the producer itself fails, we'll have enough consumers, to take, the load that I'm injecting. So we're going to give it a minute and try again. Otherwise, it's demo, demo day where it's different from what everything you've tried in the past, which is nice. So let's see. So it started again, the producer, as it should, and we're inducing some load. So in theory, while that happened, we should have gotten a few errors from one of the 3 consumer services. Let's wait for 20 seconds. Those 25 seconds are mostly for me to have a record window of data. Otherwise, it's not really useful. Verify error rate is not in a given term. So if we look back at the code, here we said we shouldn't have anything that returns a 500. So what happens was the consumer talks to the producer is not here for a split second. That triggers a 500 from the consumer service. That's what we see here. And that means when one of the pod producer actually restarted, we impacted the consumer, which is fairly expected, to be honest. But now you've got proof and you know how to actually go on about it and prove that, right? And collect data about it. And this is how you build an experiment. At this stage, what you have is now a fully running experiment that can check that every time you have a release of producer, if you have not enough pods, if you had one only, potentially you can harm your customers. So it's fairly straightforward here as an experiment. Right, I'm going to move on to the next one. I really want to give you a time for questions. This one I'm not going to go step by step because it's a bit more, a bigger one. This one is interesting. We're going to have an AZ failure. So with an extension called Chaos AZ Chaos AWS, built not by us or by me, but by an AWS engineer in Singapore. We have basically a way to fail an AZ for a load balancer and other variety of the resources, by the way. Here, what we say is we simply remove a subnet in one of, to an AZ. So assuming you know where your pod, for example, is, because we have one only, we could decide we can't access, what happens if we do that? So that's where we're going to actually go back to just one replica, and I'll explain more what we're going to do. All right. So we're going to lose. We go back to one consumer and one producer service only. We look here, and it's on that node. So we're going to see where that is. Maybe that's one. All right. So we see that we have 3 availability zones on our load balancer, and we've got enough subnets, so that's good. And now let's look at, for this node where we are consumer 213, here we are on zone B, right? So that's the zone we're going to be interested in to try for that particular demo. All right, so go back here. In the experiment, what I'm going to do is, well, it's already on B, so it's good. So what I'm going to do is remove the subnets from that zone, for that zone, basically. So load balancer won't be able to interrogate that zone anymore. And run pretty much the same experiment. The only difference here is I'm going to use CloudWatch to monitor the returns, the value returns by the service. And I'll explain that later. We'll see, I'll explain also the configuration to honeycomb and places like that a little bit later. So let's see what happens. All right, easy. Can we have watch? All right, let's see if that works. So our hypothesis went through, and now we should have only, we have now only one A and one C. All right, so we can't, in theory, we can't access consumer B. One thing that we can actually verify for ourselves. There you go. We can't actually access our service anymore. Pretty neat. We've got a fairly short file that actually generates an AZ failure, and can do that for other services as well. This one is going to take a lot more time, 5 minutes, sorry. So I'll walk you through the things of the experiment. The reason is the CloudWatch period is fairly long to get some value of interest. So that's why we do that. But you see here, I've got a blog called controls. I want to focus on that for a few minutes before it finishes. Those controls are things that you can run orthogonally to the experiment. So in a way, they allow you to run things as the experiment runs, but they are not part of the experiment. They allow you to do things like this one, for example, we have Slack. So to send to Slack, so I'll show you what that looks like. Here we have this experiment which just started, and basically it sends message to Slack with, I'll show you that, with a bit of payload. So it shows you the things directly into your Slack, team, and you can do that. We have one which is open tracing, and here I've configured it so that it talks to Honeycomb. So I'm going to go to Honeycomb and see if we have something. It might not be there because I think the trace is sent a little toward the end. Oh no, 2 minutes ago. So it's not going to be big, this one, because obviously it just started. So I'll show you one. We just have the one for the probe itself, the steady state, but I'll show you a full one so that it's more interesting. I think that's the one. That one is full. Nope. Another one. I may have stopped before. Yeah, this one is probably more full. So here you have a bunch of things where you see the method that we are running. It looks 300 seconds, 5 minutes, like we saw. It runs, and basically you've got with open tracing a very nice way of looking at your chaos toolkit experiment across time, and obviously bring your all information into it and correlate that with other events right into your system, obviously. So controls are simple pieces of usually Python code extensions that you inject, and that's what's happening here. The Reliably one, I will, if I have the time, I will show you that in a minute. So that's basically what you're doing here with those controls. Is it over now? That should be in 2 minutes. So interestingly, while it's finishing, while I was developing this experiment, initially I used the Prometheus probe here. I would never get any error. And you know what? Because the Prometheus thing was talking directly to the service, but service is fine, it's running. What I disconnected was a load balancer in front of it. So asking Prometheus for the service health was not going to give me anything because I was unplugging the load balancer, not the service itself. So it's one of those cases where you have a brain, a brain failing you a little bit. So I was creating an experiment that couldn't actually show me anything, which leads me to also say something here. Sometimes your experiments will pass. You still have to question it. It could pass because you're not impacting the system, or it could pass because you asked the wrong question. Your steady state has nothing to do with your method, and therefore there's no correlation here. So there's nothing to learn. I guess it's one thing to learn that way, but it's not necessarily the learning you probably long for. All right, so this one should finish anytime now. We should still have only. Oh yes, in this one we remove subnets. We're using a rollback here. So when you finish, put the system back to where it was, because otherwise you're not gonna be happy, and your sysadmin won't be happy if you remove AZ and you don't bring them back, right? So you probably want to make sure that for something you need a rollback. For pods, you didn't, because it's self-healing. You don't really need that in theory. But for load balancer, an AZ like that, you really want to have the rollback. All right. Any time now. Unless 300 seconds don't mean 300 seconds these days. See, demo is going to be not with me again today. Should finish. Oh, come on. That always happens, right? It works well, and we saw that with an income. At least I've got the proof it did. But obviously today, there you go. It was a little longer. I don't know why it took so long. And we see that now the load balancer tells us it's different. And it's different because, well, as we saw when we did this, and the system should be back online now, we had a 503. And because we said in the experiment, I'll go back to the experiment here. We don't want, in the tolerance, we want 0 failure. That's what I was saying. It's a bit harsh, to be honest. We probably want a bit of a slack here. 100% reliability is uncanny. But here for demo, I was, being picky. So basically, we know we had that. And if we look at journal, I think it will tell us somewhere in there. So that's the C5. We had actually 146 requests out of all of the ones we've done, which is, a lot of 140. So basically, pretty much all requests have actually failed with the 503 because we immediately add the load balancer failed, obviously. So here we with a simple file again, we've proven that our load balancer, if it loses an AZ, it can have a problem. And I'm not going to run that because we are too short in time. But if I increase back here this and I go back to 3 replicas, because I've set up the replicas to be distributed across nodes and therefore across AZ, it's not going to happen again. So if I run that experiment again, it will pass, because the load balancer simply ignore that AZ and send that to something else, obviously, as it should. So it's pretty neat. You can prove and you can play with that and see, what is the right threshold for you and things like that. So with a simple file again, you've done that. Finally, before I finish, and I will not bother you too long with that, unique chaos management, because I've got a bunch of chaos experiments here. And one thing we're working on at Reliably is a way for you to run that. So I'll go back to, well, I'll run it, no worries. We're going to run that as a plan from here. So I'll pick that. I'll explain that in a minute. And what that does is it has scheduled because that thing is in the middle of what it shouldn't be. All right, you're annoying. Actions. So what we've done with Reliably here, we said we need a dashboard, we need a central control tower of your experiments. We need to be able to store them, make them, visible, and available to all, and see what happens, when, across the organization, obviously. But we didn't want to run that on our premise because you already have things. There's a lot of secrets. Chaos engineering is a sensitive thing, obviously, so you don't want us to run from our side and have a big door open for us to actually poke your system. But what we do here is we work towards creating runners, and this one is the one we have on GitHub, where when I created the plan, what it did was submit a GitHub action to run that experiment and use one of the GitHub environment secrets, bag, and it runs the experiment for us here. So it installs, all the chaos toolkit dependencies, and it runs the experiment. I don't know what GitHub is doing here. Sometimes it's flaky. So I'll show you another run just to show you what it looks like. One that worked, might as well. So what we see here is it ran the experiment on your behalf from there. So we are going to implement things where we have runners in GCP, in AWS, with a variety of runners. So you'll be able to provision runners, and just we'll hook into them, and you'll control everything you want to, all the permissions, everything you need to run that. Here, what's interesting with GitHub is you still can have a runner in GCP or other places, and you still own the thing. Secrets are stored on GitHub, so they're not stored with us. So really making sure that we don't own, first of all, your data, and we don't own your secrets. We don't want to do that. So we're interfacing with those systems to run that on your behalf. And what we do is once we've run that, we store the, let's pick one that ran. And this one is not good. Maybe this one. You've got the experiment that was run, and if I could find one that has succeeded. So it runs the experiment, it stored the experiment, the action, that's what we stored. And then it stores as well the journal. So I just need to find one where we've got that. There you go. So it stores the journal as well. So the result of the chaos engineering experiment, you can do then whatever you want, and the chaos toolkit log so that you can see what happens. So the idea is with Reliably, you can organize your runs and deploy them wherever you want, so that you control the data, you control the runner, you control the environment, and we don't have to own it. So we support GitHub, we're going to support other cloud providers, and so that you'll be able to run Chaos Toolkit experiment from a central place, but you basically completely own everything on your side, so that we don't have to see your data, sensitive data, more than you issued anyway. So yeah, that's all I wanted to show you. I'm sorry if I went very fast, but we're already at the top thing, and I wanted to give you an opportunity for questions. But what we saw here is Chaos Toolkit is versatile, it's very extensible, and it allows you to run things in a variety of ways that hopefully, is going to suit your system, data centers, anywhere you need to run it. Chaos Toolkit will abide. Obviously, extensions sometimes don't exist, so we have to build them. But usually, it's fairly trivial. It's just a bunch of Python functions gobbled together anyway. So please feel free to, I've finished now. Please feel free to raise your hand and ask any question. Maybe I see the chat was, there were things, on the chat. So I don't know if there were questions already. Otherwise, feel free to just switch on your video and ask any question. I'll be happy to see if I can answer them. And don't be shy, by the way. I've spoken so much. I would be very pleased if someone could take the microphone for a minute. Nobody? Everyone is shy, or everyone is gone to lunch already, or or maybe I was that clear that there is no questions. It could happen.
Yeah, it's a good time for lunch. Yeah. Hey, Sylvain. Pleased to meet you, by the way. I know we've spoken in the channel, but yeah, I find it nice to meet you. To be honest, I don't have any particular question regarding the presentation. More of like from the Chaos Toolkit landscape perspective, with my client, we are trying to set up basically a chaos engineering program, and we run in AWS using ECS. And one of the difficulties that we found is that it seems like most of the chaos engineering tools are designed to be working with Kubernetes. So every time you need to run anything in ECS, especially if you use Fargate or any other provider, it's quite hard to find tools. I wonder if you're in touch with somebody that has the same situation, like they don't typically run with Kubernetes. That'd be good to maybe get in touch with somebody or collect any feedbacks or previous experience tools that has been used for this situation. It would be a very good conversation from our perspective. I don't know if my question was clear, but
no, I think it's a call for the community to join and discuss. Definitely, I think it makes sense. And I, Manuel, indeed, we have talked quite a few times already on Slack. I think I've seen people using against ECS, or at least within ECS, but interestingly, a lot of things that I've seen people applying chaos engineering and Chaos Toolkit, the chaos engineering in general, are people moving away from their old. Don't take that as a wrong way, but moving to Kubernetes, whether it's wrong or right is not for me to make a decision. But in sort of that migration, people wanted to bring that. Is that they could go to chaos engineering because the tooling is more focused on Kubernetes? I don't think we are specifically, but I'll be honest, I'm not also an AWS user, hardcore user. So there are plenty of things I'm sure I'm not covering, and I would love to know, because I'm happy to help, but because I'm more of a Google Cloud user, sometimes AWS things are escaping me. So definitely we should trigger the conversation on Slack. I'm sure the biggest community is AWS for Chaos Toolkit anyway. So there must be someone who's having a similar setting as you.
Yeah, but it would be a good conversation indeed, maybe to kick off in the Slack channel, see if anybody else in the same situation can weigh in. But yeah, most of the time, like especially for like very specific attacks on CPU, memory consumption, and this kind of things, we do rely on FIS anyway. So we decided to go with Chaos Toolkit because we have a lot of tools to generate like loads. So we from the test environment, we can implement Python functions. So that on your point about like Chaos Toolkit being very flexible and with just writing a couple of Python functions, you can pretty much do anything. So that's especially the case for us. I can confirm that's why we decided to use it in the first place. And then obviously, if we ever want to use anything else, like any other Chaos Toolkit framework or FIS in AWS, we're free to do that by implementing a function or maybe use something from the Chaos AWS. So that was a good option for us. I was wondering more like, okay, what set of tools like people use when you work outside of the Kubernetes realm? But yeah, thank you very much. That answered the question.
All right, thank you very much. Well, I think Bram is echoing what you're saying about the system being very case oriented. I think it's why we never actually gear towards Kubernetes only. We do support it, but cloud native is very Kubernetes, and I guess for a lot of companies commercially aware, it probably makes sense as well. It's where basically cloud native is going to invite newer techniques, newer tools. So probably that's where you want to be. But interestingly, just for the crowd here, a lot of people talking to me are still in data centers. Because they can't go to the cloud yet, or a lot of people are not using containers or even Kubernetes at all. So I think not necessarily AWS specific, but there are plenty of companies that are just not there yet. So I think Chaos Toolkit does provide a nice option there, but it does have the downside of a lot of hands-on. Basically, you really need to dig into it. It's not as friendly as a Gremlin. It's not as friendly as other tools, but it's much more extensible in a way. So what you lose on one end, you probably win on the other. So it's there is a bit of for everything, but we've seen a lot of people coming to us because we support virtually anything because the tool doesn't have a mindset of its own for that. But obviously, sometimes it means you do actually implement that yourself. I think we are at the top of the hour, or at least at the top of the demo, right, Adele? So if anyone has any other questions, feel free to join our Slack and ask there because, well, I tend to be there quite a lot. But otherwise, what people do when I don't see something, they DM me. So I have more DMs and channels on that Slack. So feel free to reach out because I'm always pleased to have a conversation with users, clearly. So feel free to stop by. But I always love when the community discussion is public. I think it benefits everyone as well. All right, thank you very much. Adele, maybe I'll give you back the microphone.
Yeah, no, thank you so much, Sylvain, for the demo and sharing all of the insights today. As you mentioned, we've put the Slack link in the channel in the chat, but we'll also be following up with everyone. We'll get an email sent out so people can join there, and obviously they can reach out to you on your LinkedIn, but also on the Slack. That'd be great. So thanks everyone for joining us, and we hope to see you again real soon. Take care, everyone.